Section 4.5, 2 by 2 matrices, determinants, and inverses. In this section, we're going to look at the determinant of a 2 by 2 matrix and finding the inverse of that matrix. And then we're also going to use inverses of matrices to solve matrix equations. I want to start this lesson by posing a couple of questions for you to think about as we go through this lesson. The first question is just a basic review. Can you solve an equation like 3x equals 24? What operation would you use, and how would you find out what x is? So after thinking about that kind of an equation, I want you to think about this equation. A matrix equation involving multiplication. How do you think I would solve an equation in this format? If I were to tell you that in matrices we don't have a division operation, what is an alternate way that you could solve 3x equals 24 if I didn't allow you to use division? Now, if you think about this for a minute, what I would use if I wasn't allowed to use division would be my multiplication by the reciprocal, or the inverse. Now, obviously, with a matrix, the inverse of a matrix is not going to be the same as the reciprocal of a number. So we're going to have a different way of finding the inverse of a matrix. And that's what we're going to start off with today. How can I find an inverse of a matrix so that I would be able to solve an equation like this one? Okay, so two things about the identity and inverse of a matrix. First of all, the multiplicative identity of a matrix, which we would normally call the reciprocal when we're talking about the multiplicative identity for real numbers, is going to be a square matrix that we call I for identity, that has ones along the main diagonal and zeros everywhere else. So let me give you a couple examples of what that would look like. Okay, so it has to be square, which means it has to have the same number of rows and the same number of columns. And then it says that we have to have ones on what we call the main diagonal. So I would start with a 1 up here in the corner. And if I'm going to do a 2 by 2 matrix, that means 2 rows and 2 columns. Okay, so if I have an identity matrix, then I have ones down the main diagonal and zeros everywhere else. Okay, so that's a 2 by 2. If I do the same thing with a 3 by 3 matrix, again 3 rows and 3 columns, it's going to look like this. And you can see my ones going down the diagonal of that one. So this would be a 3 by 3. Okay, and you get the picture. You could do this with a 4 by 4, a 5 by 5, any matrix as long as it's what we call square, having the same number of rows and the same number of columns. So just as in real numbers, identities and inverses have a relationship with each other. When I talk about the multiplicative inverse, there's no specific inverse of every matrix like there is an identity matrix, but it talks about having two matrices called A and X. And if they are square matrices, and A times X is the same as X times A, just like we talked about in the last section, multiplication is not necessarily commutative when you talk about matrices. If you multiply them and they equal the identity matrix I, the ones down the diagonal, then X is called the multiplicative inverse of A. Or we note this with this notation that says A inverse is how I would read this. Okay, so now in general, what that means, I'm going to use a 2 by 2 matrix here, but if I had a 2 by 2 matrix that I multiplied times another 2 by 2 matrix, since I know that it's 2 by 2, if they are inverses, then I would have to get the identity matrix that looks like this when I'm finished. Okay, so one 2 by 2 matrix times another 2 by 2 matrix gives me the identity matrix of a 2 by 2. So ones down the diagonal, zeros everywhere else, those two would be inverses of each other. Okay, so let's test that out a little bit. We're going to verify that these two matrices are inverses, and verifying just basically means to prove, and I'm going to prove that by multiplying them together and showing that they are actually inverses because I get the identity. So I'm going to start this with multiplying. And remember, when I multiply rows by columns. Okay, so I'm going to start with row 1, because I'm doing A times B. I'm going to start with row 1, column 1. So 2 times 2 is 4, 3 times -1 is -3, 4 and -3 are going to give me 1. Then I'm going to do, repeat this process, and I'm going to do column number 2. 2 times -3 is -6, 3 times 2 is 6, so I'm going to get a 0. Okay, now I'm going to come back here, and since I'm finished with row 1, I'm going to repeat this process with row 2. So row 2, column 1 is 2 times 1 is 2, 2 times -1 is -2. Those two together are going to give me 0. Okay. Then I do the second row, second column. 1 times -3 is -3, and 2 times 2 is 4. So -3 and 4 is again 1. So far so good. When I multiply A times B, I end up with the identity matrix of a 2 by 2 matrix. Okay. Now, this next time, I'm going to have to change my multiplication so that it's B times A, which means actually that matrix B goes first. So I'm going to rewrite these so that we're a little less confused about what's going on here. So we'll put matrix B first, then times matrix A, which is 2, 3, 1, 2. And if these are really inverses of each other, when I switch the multiplication, I will still get the inverse matrix. So again, we're going to do rows times columns. So 2, -3 is multiplied times 2 and 1. So 2 times 2 is 4, -3 times 1 is -3, 4 and -3 make 1. Then I do the second column. 2 times 3 is 6, -3 times 2 is -6. That makes 0. Okay, so I'm done with the first row. Now I'm going to do the second row. -1 times 2 is -2, 2 times 1 is 2, -2 and 2 are 0. -1 times 3 in the second column is -3, 2 times 2 is 4, -3 and 4 is also 1. So by doing my multiplication, I have proven that A and B are inverses of each other. So you could say that B is the inverse of A and A is the inverse of B. Okay, so since determinants are part of a matrix, and it serves two purposes. First of all, a determinant will tell me whether or not a matrix is actually able to have an inverse, and then in the process of finding that inverse matrix, I actually have to use the determinant in finding or writing the inverse matrix. So to find the determinant, you'll see up here at the top I have a formula. It says the determinant of A is equal to A times D minus B times C. Now, if you really look at that, what it does is you multiply at a diagonal here, A times D. Okay, so that's AD right there. And then, get a different color for just a minute. We do B times C right there. And we take those two results and we subtract them. So, the determinant down here, I'm just simply going to start by multiplying -3 times -5. So I'm going to take -3 times -5. Minus, I go the other way, 4 times 2. So -3 times -5 is 15. Minus 4 times 2 is 8. 15 minus 8 is 7. So the determinant of this matrix is 7. Tells me that as long as my determinant is not 0, then there's going to be an inverse to this matrix. So having a determinant of 7 tells me that this matrix does have an inverse. Okay, so let's try that again for this next one, just to get a little more practice. So multiply together as a diagonal, so 8 times 3 minus, multiply the other way diagonally, 7 times 2, which is 24 minus 14, and 24 minus 14 tells me that my determinant is 10. So again, that tells me, first of all, that I know I have an inverse that exists for this matrix. Okay, so once you know that it exists, we need to actually find it. Okay, so if I need to find the inverse of the matrix, then I am going to use that in a formula to find the inverse of my matrix. So you see here my formula. It says if my matrix is A equals A, B, C, D, then the inverse of A is equal to 1 over the determinant of A. So I found my determinant in my last step. And then I have to do a little rearranging of my terms in my matrix before I do my multiplication. So you'll notice two things. Okay, I want you to notice on this that your A and your D switch places. Okay, so you look up there at the top, A and D have switched places. The other thing that I want you to notice is that B and C didn't move, but they become their opposites. Okay, so if they were positive, they become negative. If they were negative, they become positive. So let's look at how we would use this to actually find an inverse. Okay, so we're going to find the inverse of M here. So the first thing I want to do is figure out the determinant of M. I want to know go. I want to know if this actually has an inverse. So to find the determinant, I start by multiplying my diagonals. -2 times -4 minus my diagonal the other direction, 2 times 5. So that's going to be 8 minus 10 makes my determinant equal to -2. So since that's not equal to 0, that tells me that this does have an inverse, and I will be able to find that. Now, according to my formula, if I want to find the inverse of M, I need to take 1 over my determinant. So that's going to be -1/2, and I'm going to multiply that by by my matrix. I got to move my terms around. So A and D swap places, so it's going to be -4 and -2 like this. And then B and C don't move, but they change signs. So that becomes -2 and that becomes -5. And then from here, it's just a scalar multiplication of taking everything times a -1/2. So -4 times -1/2 is going to give me a +2. A -2 times -1/2 is going to give me a +1. A -5 times a -1/2 is going to give me a +5/2, which you could also do as 2.5, 2.5. And then lastly, -1/2 times -2 is again +1. So the inverse of this matrix M is 2, 1, 5/2, and 1. And I could check that by multiplying the two matrices together and make sure I get the identity matrix. We will continue our conversation about matrices and their inverses and using the graphing calculator with matrices next time I see you in class.